This is the Beyond Satisfiability workshop at the Simons, which is we're running now as a virtual weekly seminar instead of a focused workshop during the week. And so this Tuesday, our speaker is Ambros Gleixner, who is heading the mathematical optimization methods group at the Zuse Institute in Berlin. In particular, this group has produced the SKIP mixed integer programming solver and the Simplex linear programming solver, which I guess has a fair claim to being like the best academic MIP solver, I guess. Can I say that, Ambros?
Yes, I would say so. So SKIP definitely is the fastest that you can obtain in source code, where you can look at the source code.
And I guess it's also fair to say that this research group has been also feeding quite some talent into places like Gurobi and Simplex, where they add a few commercial secrets that mere mortals cannot be privy to.
Quite a lot of previous SKIP developers are now working for Gurobi, Simplex, FICO, and some others of the new MIP solvers that are currently coming up. It's quite an active field, I have the feeling, also with Asian players entering the market. So it's exciting.
So yeah, and this is what Ambros will tell us about today. I think there's going to be like a somewhat of a gentle introduction to MIP solving, and then get into more and more of the details. And in particular, I'm hoping that we'll get to talk of some of the challenges for how to deal with floating point issues and do exact MIP solving, and also how to certify correctness of results for MIP solvers, which has arguably been a bit of a maybe weak spot so far. So without further ado, Ambros, please.
Yeah, so thank you, Jakob, for this kind introduction. Yes, so it is definitely true that in the classical mixed integer programming community, I think the drug has been the need for speed more than the need for being like 100% exactly correct. Also, of course, numerical stability is very high on the agenda, because these MIP solvers are heavily used in practice, and lots of ill-conditioned data is thrown at them, and they are amazingly stable with this regard. But yeah, my personal interest is also to be even more strict in a mathematical sense of exactness, and to develop algorithms where you get an exact and certifiable answer. And here in the title, I've written exact mixed integer programming over the rational numbers. And yeah, let's see why this is important for the algorithms that I will present. So the title of the workshop is Beyond Satisfiability, and I think mixed integer programming perfectly fits that theme. Here is a very overloaded slide of a few points that I wanted to mention in the beginning. So obviously MIP is a generalization of SAT, and it is so for several reasons. So first of all, we do have an objective function. Our main goal is mostly to optimize a linear objective function that is different than SAT. But not only that, additionally, we have more general types of constraints. So any linear inequality or equality can appear. And here in this notation, I've written it in matrix notation, AX less than or equal to B. But obviously, this is just a list of linear inequalities or equalities, nothing fancy. What I've pointed out is that rather important is a special type of constraints, and these are the variable bound constraints. And that also points to a third point in which we are more general than SAT, the types of variables that appear. So we do not only have binary variables, although in the most typical applications, binary variables modeling yes and no decisions are vital, and the solvers are heavily biased towards performing well on problems where binary structure appears. But not only so, variables can be general integer. That means they have larger bounds than 0 and 1. They can be continuous and take any value in the real numbers. And the bounds can even be missing. So there may be unbounded variables among them, which also, as we will see, can create some trouble when you want to solve these things exactly. So yeah, I've written here that the continuous variables are from the domain of real values. But one thing that is nice is if the input data is rational, and by that I mean if the objective function C and the coefficients in the constraints and the right-hand sides and the bounds are all rational values, then a rational answer always exists. So I mean, there are actually 3 types of answers that a MIP can have, right? One, it could be infeasible, that the constraints are contradictory. Then it could be unbounded in the sense that arbitrarily good solutions can exist. So solutions with arbitrarily small objective value, or the problem is bounded and there is a finite optimum. And in the last 2 cases, we actually always know that a rational optimal solution exists. Why is that? So in the bounded case, so when you fix the integer values to a certain value, and then what you obtain is a linear program, and this linear program always has a basic solution. We say this is a solution where a number of constraints hold with equality, and so we can determine the solution values by solving a linear system of equations. And if the coefficient matrix and the right-hand side is rational, then also the solution will be rational. And so although there exist irrational answers, we can restrict ourselves to rational ones. And the nice thing is that we even know that these rational answers can be chosen to have polynomial size in the encoding of the input data. So if we restrict ourselves to these basic solutions, then they will not have exponentially large denominators or enumerators. Yes, so maybe to say something about the visualization that you see on the right. So mixed integer programming is definitely above Z. Important subclass is, of course, if we do not have any continuous variables. So we say we have just an integer program, or if we have no integer variables and then we are left only with a linear program. So linear programs are interesting in itself, but also for solving mixed integer programs, as we will see, because they appear as subroutines in the classical LP-based branch and cut algorithm. So of course, there are further generalizations. You can allow for nonlinear constraints, which brings you to mixed integer nonlinear programming, or you can even go further and allow holes in your domains or other general types of constraints. Then you would end up in the field of constraint programming. So maybe just a bit of history. The solver skip that has come out of Zuse Institute was initially started in order to form a combination of, yes, mixed integer programming techniques, satisfiability techniques, especially conflict-driven closed learning, and techniques from constraint programming like domain propagation, and the, say, problem class that using all these combinations of solving techniques we can solve efficiently in a branch and bound framework was coined constrained integer programming. So this is not so much of a program of a problem class, but rather of an algorithmic concept which tries to integrate these different techniques. This integration has become pretty standard today in mixed integer programming solvers. So Skip is not the only solver that does that. also others have taken over things like conflict-driven close learning into their repertoire. So maybe also to compare to SET, so the appeal of mixed integer programming is, yeah, they're the same and different reasons than what makes SAT solvers appealing. So also in the MIP community, we have black box solvers. That's quite nice in practice because modeling and algorithm design is separated, and we have experts that deal with solving these and experts that deal with modeling. And that also helps bring them into practice. But also most of these solvers are, yeah, open box in the sense that you can extend them by problem-specific techniques. Skip as an open source solver is, of course, a prime example for this, but not only, also closed source commercial solvers have a tradition of allowing to add supplementary techniques during the solving process. So this has made it quite attractive also for academic researchers to use some of these closed source solvers and to do research with them. Then special point is maybe that MIP solvers provide global optimality guarantees to their answers. So we do not simply find good solutions that are feasible and have good optimal objective, but we always, even if the solution is not successful completely, provide a guarantee on how far the best solution could be off from the solution that was found. And that allows two things. So first of all, you can use these solvers as heuristics. You do not have to run them to global optimality, but you can also use this gap that you get in order to stop early if you do not require higher, say, precision in the sense of objective quality. And so that has made them quite attractive also in practice.
So two questions. So one,
yes.
this fact that you have is somehow a feature of how the MIP algorithms work, that you always maintain like both an upper and a lower bound, and then they get closer and closer.
Exactly. Yes, correct.
And then Armin Bera asks, when we talk about polynomial like the solution in polynomial size in terms of the input, this is in terms of bit size, like polynomial number of bits in? Okay.
Yes, so if we represent the numbers in binary encoding, yeah.
Okay, thanks.
So we have kind of logarithmic input size is logarithmic in the actual numbers, and the output size is measured, of course, in the same way. Yeah, so please always interrupt me. I cannot see the chat here while I'm presenting, but do not hesitate. Jakob has already mentioned it. So the special topic of this talk is actually how do we solve this without any numeric errors. But I think before I can do that, as the first talk who talks about mixed integer programming, I should give at least a short introduction to the algorithmic paradigm that I'm considering. That is the state of the art for most MIP solvers. And this I will do in the first section, and then in the second one present the sort of the trouble that we are in when we use floating point arithmetic, and give a short overview of what has been done so far. So what are kind of the fastest algorithms that guarantee exact results so far? I mean, until like beginning of the year, because we've just recently published a new version of exact skip, an exact version of the skip solver that improves upon this in several aspects, and that will be the content of the third section. Then I would conclude this first part of the workshop today with the conclusion. We can have some discussion. And then, yes, we are open to dive deeper into two topics. The first one would be how to actually solve linear programs exactly. And the second topic would be how to verify the results that such an exact MIP solver gives certificates. And I'm perfectly fine to skip any of these. We will see after the conclusion, I guess, how to continue. So let's get started with an introduction to MIP solving. So MIP is NP-hard, and so the common approach to tackle such problems would be to, not directly try to solve them, but to compute, first of all, bounds on the optimal value, and bounds of two types, of course. So one would be an underestimation of the optimal value. We also call this a dual bound. That is obtained typically by relaxation. So we increase we relax and remove some of the restrictions on feasibility. And classically, how we do that is that we remove the integer restrictions, so all variables become continuous. This way we obtain a convex optimization problem, which is theoretically fast to solve, but also in practice often it works quite well. And this gives us a solution, both an actual solution, which is infeasible because some of the variables are fractional, but also a lower bound on the objective function value. And then the second bound would be an upper bound. So if we are lucky and find a feasible solution that satisfies all constraints and the integrality restrictions, then we have a bound U. We call this the primal bound as well. This is obtained by in two ways. So first of all, we could be lucky and the LP relaxation is accidentally feasible. Then of course we are optimal at the current point. So maybe with some, for looking at some subproblems. So not optimal for the whole problem, but also there are in these solvers implemented a lot of supplementary techniques, so-called primal heuristics, which try to find good solutions, but have no guarantees on doing so, and are also trying to be fast in the sense of not being shy to fail if it doesn't look good. And yeah, when you have now these two types of bounds, what you can then implement is a classic divide and conquer approach. So this gap that you have between the upper and the lower bound, U minus L, can be systematically reduced by subdividing the solution space. And how this is classically done is by taking an integer variable that takes a fractional value in the linear programming relaxation, and use this to construct two subproblems. One where you say less than or equal to the round down, one where you say the variable must be greater than or equal to round up. And since we have finitely many values, and if the integer variables are bounded, then this converges. Schematically, we always look at this like a branch and bound tree, which is here on the left-hand side. If we go down to the subproblems, then this is applied recursively. And as I already said, if we are lucky and the linear programming relaxation is accidentally integer feasible, then we find an improved upper bound and a first feasible solution. And if we stop at some point after this, then even if we have not converged to a gap of 0, still we have an answer that can be implemented in practice. And we even have a gap that tells us how far we may be off from the optimal objective value. Yes, so in this animation, we don't find the optimal solution at the first time, but only when we consider one of the later nodes. The schematic view on the left-hand side is, of course, not very accurate. So here is an attempt to visualize this process a bit better. This is a branch and bound tree where in the XY plane, we have used multi-dimensional scaling to project the linear programming relaxations that we obtain during the branch and boundary at each of the nodes, which of course live in a very high dimensional space, to project that to 2D. So multi-dimensional scaling tries to somehow preserve the distances. And so what you see there at the very bottom are these projections of the linear programming relaxations. And then in the Z direction, going up, you see these linear programming relaxations aligned with their objective value. And they are connected in the same way that you would connect them schematically in the branch and bound tree sketch. So at the very bottom, you see the initial node, which we also call the root node. It has, the lowest, the worst dual bound that we find initially. And then you see this lower bound L, the dual bound, increases as the algorithm progresses. And the first thing, so I'm not sure, can you actually see my mouse pointer here?
Yes, we can see your mouse.
So this is here the root node, and then first of all you see a line that doesn't even divide, but just goes to kind of a second root node. What happens here is that we improve the tightness of the relaxation. We'll come to this later, and obtain in a better lower bound. But then starting from here, actually this branching happens. You subdivide into two different subproblems by probably branching on a binary variable, fixing the value to 0 and to 1. And you see also here the lower bound increases slightly, and this continues recursively. And the green, the green lines here indicate the level at which the optimal integer objective lies. You see that some of the nodes here exceed this optimal objective. This is quite natural. So when you fix more and more variables, your dual bound gets worse and worse. So it increases, and it may even increase to a level which is suboptimal. So such that in the subtree below, you will not find the optimal solution anymore. And if you already know an upper bound U and you've exceeded this upper bound, then you know that you can stop this search. So you do not need to complete your enumeration. This is called pruning. And this is, of course, one of the things that makes this whole approach even feasible. I would say if MIP solvers are successful, then usually this happens because they somehow tricked out the usual exponential blow up that you obtain for NP hard problems. And one of these tricks is, I mean, it's not a trick, but a systematic thing, that you can prune subtrees that are proven to be suboptimal because of the LP bound. So this is just a very quick run through this branch and bound paradigm. But let's look at what happened here at the very beginning. So where I said we are not even branching and the lower bound improves, how can this happen? Well, the most important way this happens is that we add so-called cutting planes. So this you see here on the right side, where the blue region, or let's start like the blue dots, are all the integer feasible points of our problem. The blue region now is kind of the tightest, the convex hull of these integer points, so sort of the tightest polytope that we can lay around these integer feasible points. But unfortunately, it is the case that the linear programming relaxation that we obtain when we drop the integrality requirements is not this tightest relaxation, this blue region, but it is a bit larger, and you see it here indicated by this gray line. So this is not surprising, because if we would get this blue region for free, say, then somehow MIP would be easy. We would just solve the linear program. We would arrive at one of these vertex solutions here, and these vertex solutions would always be integer feasible, and then we would be done in polynomial time. That cannot be the case. So usually we obtain a point like this in red, which is further away from this convex hull and has some fractional components. And now I already said the standard way of, or what branch and bound does is it resolves this fractionality by subdividing the problem into two parts. There is another algorithm to do so, to kind of remove this infeasible fractional solution from our relaxation. That is to add a cutting plane, which is a inequality that is valid for all of the integer feasible solutions, but is violated by the current LP solution. As a matter of fact, this cutting plane approach could be run exclusively. So as a matter of fact, historically, the cutting plane approach predates the branch and bound approach in the scientific literature, which from our point of view today is actually quite interesting, because branch and bound is, first of all, a bit simpler, you would say, from the idea and the theory behind. And second of all, it's somehow a bit more successful, even in practice. But this cutting plane approach could be run purely, so you could just iteratively add cutting planes, and you would know that with certain types of cutting planes, which are called Gomery cuts, you would in finite time arrive at an integer feasible point. Yeah, but what actually works best in practice if you combine these two, so you add some limited number of cutting planes at the root node, but also sometimes at the local nodes of the search tree, and by this you improve the dual bound. You avoid some of the exponential blowup that you get by branching, and in combination, if you do it smartly, yeah, you strongly improve upon plain branch and bound. So one reason why this works is because, yeah, the solution of linear programs is fast, and there's a bit more to that which I want to make you aware of, also to yeah, put into perspective the algorithms that we will see later for solving MIPS exactly. And this is that we are not using any linear programming algorithm. There are many out there, but typically MIPS solvers use the Simplex method. And the reason is because Simplex can warm start. So it's not only fast to solve the initial LP relaxation, but there's a huge speed up when you solve the relaxations of this, the nodes where only few changes have happened to your parent node. These few changes are usually just one bound change, right? The bound of one variable has been changed, or one additional valid inequality has been added. And here is an experiment that I've conducted quite a while ago about the average number of iterations that the Simplex algorithm needs to solve LP relaxation. This is averaged over a larger test set. And what you see here on the left is a table, how many iterations you would need at the root node and at each depth level. And on the right side, you see yeah, how many nodes there are actually at each depth level. So you see that over this test set, you kind of have the broadest frontier at about level 18 or something. And after that, the effect of pruning kicks in heavily. So either pruning by suboptimality, which I've explained before, or because simply the LP relaxation becomes infeasible because integer variables have been fixed to values that do not allow feasible assignment anymore, and this is yeah, recognized. And now if you compare the average number of iterations, 383.7 at the root node, and 3.3 at level 17, where you have the broadest width of the tree, then you get approximate like over 100 times speed up from root node to this LP relaxation solved inside the tree. And this is really one of the sometimes overlooked reasons why MIP works. So I said already, it works when we're kind of cheating the exponential growth through some special techniques that, some tricks that work for the type of formulations that we encounter most often. And the second reason is because the Simplex, and not only the Simplex algorithm in general, but also the heavily optimized implementations that exist today are so good in this re-optimization such that they can actually enumerate a large amount of nodes. Obviously, maybe I should say that in that context, this is nothing compared to satisfiability solvers. SAT solvers have much higher node throughput and explore many more nodes than MIP solvers. But when you compare it to, say, other mathematical optimization solvers, then this is still very notable, and it is crucial. So if we could even further speed up the LP solution, many more MIPs that are unsolvable today would be in reach. So this is one, there's a significant amount of MIPs where the LP solving is the actual bottleneck to reaching global optimality. All right. There are two more topics that I want to mention, and
a question.
Oh yeah, please.
So a question is it like clear that, I mean, could you also say that, well, I don't know, suppose that you had like more clever branching or sophisticated conflict analysis, then maybe you would need to solve like fewer LPs, or it's like?
Yes, obviously. So this is a combination of things.
But you're saying like given if you want to like identify a bottleneck in the current setup, then like faster LP solving would.
Yeah, I mean, I don't want to say this is the only bottleneck at all. I just want to say there are instances where which we could solve if we solved this bottleneck. So this is a limited. So I just want to point out the importance of this speed of of LP solving. It's not an exclusive bottleneck at all.
Fair enough. Okay, thanks.
Obviously, if you would have if you had a magical oracle of cutting planes or generating a tight formulation, we would be solved at the root node. Then usually, we wouldn't have maybe a problem with solving LPs in the node. Yes, that is.
I mean, there's an interesting parallel. I don't know to what extent there has been like the interactions between MIP solving and SAT solving in this regard. They're also called look-ahead SAT solvers. That we had a seminar, I think, in one of the workshops a few weeks back, where the best SAT solvers that are used for like, for instance, for hard combinatorial problems, they typically don't do this conflict-driven close learning paradigm where you just make decisions quickly and then backtrack and do conflict analysis. Instead, they spend like huge amount of time on probing and setting different variables, collecting statistics. Like if I set this variable to true and false, how will my subtrees compare, and how much does this thing? It seems a little bit like what I think you call strong branching. Like you would actually try to set every variable to like true and false, and then really investigate how this works and spend lots of time to compute statistics, and only then the look-ahead solver commits. And somehow my understanding, I'm not in this area at all. I think some people in the audience, like Armin Bira, it seems like to be here, could correct. But my understanding is that you spend tons of time on this look-ahead solving, but that helps you to, at least heuristically, like keep the decision tree depth shallower because you're making so good decisions. But
yes, so and maybe this is also something to mention for MIP solvers. MIP solvers spend much more time at a node, and so we also, in advance, I think we spend more time to really try to figure out the right decisions, like in branching, in order not to create extra work. because just restarting like in SAT or in conflict-driven close learning is so much more expensive in MIP that it's not feasible in the same way. Yeah, I think that's a nice parallel.
Mm-hmm. Thanks.
So yeah, there are two more things that I want to point out. I mean, why these MIP solvers work in practice, because they have many additional supplementary techniques. And I picked now two because this is something where we made now an advancement in respect to exact solving. The first is pre-solving, which goes a bit in the direction of what you mentioned currently, I believe, also. And the second one is primary heuristics. So pre-solving is an important phase in classical MIP solvers to improve the formulation. It's in some sense something that has a similar goal like cutting planes, but works even earlier. Here's a small example to motivate this. So there's one technique called coefficient strengthening on a small problem. Here on the left side, you see a two-variable problem. Again, the blue region is, oh no, actually not again. So here the blue region is really the LP relaxation, which you see is not the convex hull of the integer feasible points, which are marked in black. And now coefficient strengthening is a very cheap technique that can figure out that the inequality can be tightened significantly to x1 plus x2 is less than or equal to 1. And then on the right side, you see actually you have reached the state that the LP relaxation is the convex hull of the integer feasible points. And so on the left below, you see that a branching tree would enumerate to depth 2 until it finds the optimal solution and certifies it. But on the right side, if we have this stronger problem, then yes, we're done after the root node, because all we need is to solve the LP relaxation, and this will be immediately integer feasible, at least if we use a simplex solver that always returns a basic solution. And so this is one of the things that pre-solving tries to achieve, like you spend very little time, but improve the formulation significantly. The second thing would be to reduce the size by simply removing fixed variables, constraints that are not tight, and the like. And then two more points should be mentioned. We also try to extract structure, so identify implications between binary variables. If one variable is set to 0, then another variable has to have at least this tight lower bound, or something like this, or mutually exclusive assignments. Not both binary variables can be set to 1. And this can then be later used during the solving process, for instance, to create cutting planes, but also other in heuristics or in other places. Symmetry detection would also be something that falls into this category. We will not focus on that in detail in this talk. Maybe the last one is also crucial. We try to improve numerics, mostly with respect to the LP solver. So the LP solver has to do a lot with finding a numerically reliable solution to the continuous relaxation. And things that hurt there are, of course, large coefficients. And so if pre-solving can reduce the size of the coefficients, it would try to do so. There are two different types of reductions that pre-solving can do. First one is just feasibility reasoning. So you do not cut off any feasible solutions, but just like in this motivating example of coefficient strengthening, cut off infeasible fractional solutions. But then there's also some reasoning that uses the objective function and may even remove feasible solutions as long as at least one optimal solution remains. So it may even cut off optimal solutions. Yes, at least one optimal solution has to remain. And yeah, so the impact of pre-solving is among as strong as cutting planes, for instance, when you do an experiment of turning it off versus turning it on, you lose as much performance as if you would turn off cutting planes. So this is really significant, not only in terms of speed, but also in terms of the number of instances that you can solve.
When you say that you actually remove optimal solutions, but you make sure some other solutions that are also optimal are still there, yes. This would be like symmetry arguments or other types of arguments?
Symmetry is one, but another one would be also if you have parallel columns. So you have like two variables which essentially have the same function, which the non-zero pattern is linearly dependent. And then you can remove one of them, increase the bounds of the other, and then in post-processing you have to redistribute the values again. And that is actually also some form of symmetry, but it's a bit different.
And is this used again? If you parallel to SAT solving, is that some of these pre-processing techniques in the very best solvers, they are also interleaved with the actual search process. So this is something that's called in processing. So somehow the solver stops and it sort of runs a pre-solving phase anew. Is this something that a MIP solver would do?
Yes, that definitely happens. So we would distinguish like terminology. We would say pre-solving is what happens before the root node. And during the search, we would rather call it propagation. But essentially, there's a big overlap. So, yes.
Mm-hmm. And then we had
maybe now I thought of a different example for this removal of optimal solutions. Well, I'm not sure if that would remove an optimal solution, but a suboptimal one. So if you have already an upper bound and you have the LP relaxation solution, then you can look at the reduced costs, which are some dual multipliers for the variables, and which tell you if I move this variable by a bit, how much worse does the objective bound get? So how much kind of stronger does my LP bound get? And by this reasoning, I can also exclude some assignments. I can say this variable cannot be 1 because then the dual bound would exceed the best primal solution I've found so far. So I can actually fix it to the other side. That's what's called reduced cost propagation.
Mm-hmm. And then there was a clarification in the chat that this the look-ahead solvers, they don't spend tons of time, but maybe linear time in the size of the formula on making decisions, whereas CDCL decisions are sort of made in logarithmic time because you're just popping stuff off a heap. So it's but it's still a fairly significant. I mean, it's an exponential difference in the speed of the decisions.
Yes. Yeah.
Yes.
Well, I mean, also in MIP solving, you have the trade-off, right? You have to trade off the time you spend. So I would also not say we're spending heaps of time in pre-solving. Pre-solving is supposed to be very fast, but we still do spend a significant amount of time. Good. And yeah, so what I already mentioned, like this reduced cost strengthening, that requires that you have an upper bound. You already found a primal feasible solution. And so this is the task of primal heuristics. There are many different techniques on how to try and get lucky and find a solution that is feasible both with respect to the constraints and with respect to the integrality requirements. I will not go through this whole list here, just want to mention what are the goals. So we want to have a solution available if the process is interrupted early and not run to full completeness. But then we also want to support the pruning. We can actually also install this upper bound into the LP solver such that the LP solver does not have to be run to optimality because the dual version of the Simplex actually approaches the objective from below. So once it exceeds this upper bound U, it can already stop and does not need to run to optimality. And then the reduced cost propagation that I mentioned is a form of bound tightening that uses such upper bounds. And so the idea of primary heuristics in MIP solvers is a bit different than if you would run a heuristic as a standalone algorithm. You're not trying to spend as much time as possible in order to be as successful as possible, but you want to realize when you have a chance and when you don't, and then you want to fail fast. So it has to be effective on average, but we need to take care that the overall effort spent on heuristics only lies at a certain percentage of the overall solving time. Rounding heuristics, I think, is something that everybody can imagine. That's a very fast type of heuristics. There are diving heuristics, which are a bit more sophisticated in the sense, or more expensive, that you round, but you don't round all variables at the same time and then realize you've gone wrong. But in between the roundings, you resolve the LP relaxation in order to return to the feasible region that is given by the constraints. And so it's more expensive, but also more successful. And then third huge type of huge class of heuristics is the class of large neighborhood search heuristics. And one example I've put up here is the relaxation enforced neighborhood search, which has a very simple and intuitive idea, but it demonstrates quite nicely also how the linear programming solution is exploited in many ways in MIP solvers, not only for the dual bound and for the branching. So here, this heuristic would look at the relaxation, and then it would distinguish between variables that already take an integer value in the relaxation. These are fixed. All the others are left as is. We reduce the domain to like the two neighboring values. So classically for binary variable, nothing would happen. But for an integer variable, you would actually convert this to sort of a binary decision of round up, round down. And then what you get is a sub MIP, which hopefully has a much smaller size. And you can just throw your own solver at this MIP and try to solve it to obtain a good feasible solution. Of course, you don't have to solve this to optimality. You apply heavy limits. But then this, if you are successful, this may correspond to an improved solution in the original problem. This is only one example of many strategies how you could fix variables and then solve a submip. All right, so what have we not talked about? We've not talked about, for instance, conflict analysis, or the application of conflict-driven clause learning to MIP. We've also not touched upon domain propagation, this reduced version of presolving that is run at the nodes. We've not really looked at cutting planes, and we've not at all touched upon how symmetry is exploited. So there are many more techniques that are sort of hidden in MIP solvers, but this hopefully gave a rough idea on what is important for this algorithmic design. Are there any questions at this point? I think this is a good place to stop and ask. All right, if that is not the case, then yes, the next point would be, what is actually one shortcoming of state-of-the-art MIP solvers today, and that is the use of floating point numerics.
So there is actually one kind of question that appeared in the chat over on YouTube, which I don't know if you want to comment on. The 0-1 problems versus general integer problems. I mean, yes. If you have a general integer and you know it's between 1 and m, then I guess you could replace it either by m binary variables or even by log m binary variables with some kind of binary encoding. Is this being done, or is it preferable to actually operate on the integers because the problem somehow changes so much if you only use binary variables? Or?
No, it is definitely done. So Skip also even has a pre-solving step that performs this automatically, like compares, replaces an bounded integer variable with a sum of binary variables, either in unary or logarithmic encoding. This is turned off by default because it doesn't seem to be good for default setting. But where this yeah, so it's, I think it simply depends on the application whether this would help. Of course, where this often happens is also in the modeling process, right? When you have a scheduling problem, you can represent the times at which a machine is run by an integer variable or by a bunch of binary variables. Yes or no, is it run at this time? Yes or no? And there, using the binaries, you usually get much stronger formulations, of course, also much larger formulations, which creates problems for solving the LP relaxations. But from a combinatorial point of view, it's much stronger. And so typically this is preferred. This is a theoretical reason. A practical reason is simply because MIP solvers contain many tricks to work particularly well on formulations which have binary variables. And many of these things that you mentioned, also like strong branching, are simply either not executed or not executed that well when on integer variables. It's just, they're a bit, I wouldn't call it tuned, they are developed towards the binary case. So there's, I would say, a good and a bad reason why, or a theoretical and a practical reason why you should prefer binary variables in your modeling if you can.
And then there's another question, which I also guess I've been bugging you about before. So if you want to get into sat solving, then we've been marketing this handbook of satisfiability that has now just appeared in the second edition, like 2 tomes of the gathered wisdom of the sat community. Now, if someone gets so excited by your talk today that they want to read the handbook of MIP solving, like, is there such a work, or what should they read to get up to speed on MIP solving?
That is a very good question. So, I mean, this is two directions, right? One is the theoretical direction, which deals a lot with the theory behind the algorithms, and there are very good books. There are very good books on this. One recent book would be just called Integer Programming by Conforti, Cornejols, and co-authors. If you would like to know about like really the tricks that are implemented inside practical MIP solvers, then there's much fewer literature. You would really need to gather it much more from publications, and some things are not even published. I think one very good way to start is the PhD thesis of Tobias Achterberg, who has designed Skip. But it is certainly not complete today since it dates back to 2007. And so I'm not aware of a handbook of computational MIP. I think it is a worthwhile project to start.
Thanks.
Yes, thank you for the questions. When we start now talking about the numerics and the floating point numerics, then let's start with linear programming. This is where kind of things get most messy, because that's where you have to really deal with the continuous variables, and not only with them, but with the integer variables that have been relaxed to be continuous variables. And so exactly speaking, optimal solutions should satisfy the constraints without violations. They should have the bound constraints exactly satisfied. And then you don't only need this primal feasibility, but of course also optimality, which is called dual feasibility in linear programming. And dual feasibility actually also takes the form of an inequality only with the transposed matrix. So what you look at are, for each variable, you look at the column in the constraint matrix. For each of the constraints, you get a so-called dual variable, a dual multiplier. And now if you form a linear constraints from this column, then the value that, or the linear expression, then this must be greater than or equal to the objective coefficient. So that's also just a linear constraint, and it's called dual feasibility. And now you have basically a pair of solution values, one for the primal side, which are the x's for the actual variables, then one for these dual multipliers, the y's, and in order for both of them to be to form an optimal solution, they must be complementary slack, we say. So kind of if the dual constraint is not tight, so if it's really larger than the objective function coefficient, then the primal bound must be tight. So then the x variable must be at 0 or 1. And also reverse, if the variable is not at one of its bound, then this dual constraint must hold with equality. And so this is what we would actually ideally want to have, but the problem is that these solvers implemented in floating point arithmetic cannot provide this. They compute solutions with residual errors. The primal constraints are violated by some tolerance epsilon. The bound constraints might be violated, and also this dual feasibility constraint. And this epsilon, if it works well, is usually chosen to be around 10 to the minus 6 or 10 to the minus 9, so rather small. But yeah, it's not 0. And what does that actually mean? So this is not an error in the space of solutions. So that's one important thing to realize. These tolerances that are used do not guarantee that the solution that you obtain is epsilon away from the exact solution. If you think about it, what it means is that the solution, the approximate solution that you got, is an exact solution for a slightly perturbed input problem. So this is also what this second graphics is trying to suggest. So you have a slight perturbation of the blue feasible region, and your floating point solution is now an exact solution to this approximate problem. Of course, in most cases, things work well, and the solution that you get is very close to an actual exactly optimal solution. But of course, it can also be that the problem is ill-conditioned and this doesn't happen. It can also be that not only these linear programming solutions are wrong, but also that you use them to compute some invalid model strengthening that could happen when you compute cutting planes, when you perform some presolving reductions, that you actually remove some integer feasible solutions that are optimal because you apply arithmetic reasoning that's based on floating point design. So how do we deal with this? I started with linear programming because getting exact solutions to linear programs is important also for solving MIPS exactly at 2 points essentially. So you may need an exact LP solver, first of all, for primal solutions. So certainly for the integer variables, you can always round them and fix them to a rounded value. But for the continuous variables, at the end of the day, you need to somehow solve the remaining LP exactly. And that's where you need an exact LP solver. The second point where you might need an exact LP solver is for dual bounding. And that would, of course, be one of the naivest, the most simple ways how to create an exact MIP solver. simply to solve all of the LP relaxations that you obtain with an exact LP solver. That's possible, but it is quite expensive, but it would be a baseline implementation kind of. So how would we solve LPs exactly? Why is that expensive? Well, the simplest idea would be to just not use floating point arithmetic, right? But to use exact arithmetic, which is rational arithmetic if we're talking about rational input data here. And there are several implementations out there that simply implement a simplex method with rational arithmetic, and that guarantees you exact results. But of course, this is potentially very expensive as the size of the problem grows. Well, actually not as depending on the problem size, but rather as the size of the numbers that you encounter in the algorithm grows in encoding length. So what you do during the simplex method, and what somehow inherently you have to do with many LP methods, is you need to invert matrices. So in the simplex method, you get a linear system that comes from the tight equalities, which gives you a linear system of equations. And when you solve that, you essentially create a matrix inverse, and there the encoding length of the resulting solution can, although it is somehow polynomial in the input data, it can be strongly increased. And if this happens, then this naive approach will be very slow in traversing such solutions. So one thing that people have realized is the simple observation that floating point solvers are actually not that bad all the time. So, and even if you, especially if you use a simplex method, they even give you some discrete information, exactly what we call the basis information, so which inequalities are tight. And so here in the right picture, that would be the dashed lines. And if you would now solve this linear system of equations exactly, you would obtain potentially, and very often empirically, that's the case, an exact optimal LP solution. So you don't even, you simply ignore the approximate floating point solution that the solver has computed, and you just recompute exactly. And that's of course much faster than using, like doing a full simplex method in rational arithmetic, right? You just do the floating point version, which is fast at the beginning, and then only the result is checked. Of course, that can go wrong. So the picture that you see here is not always that nice. The basis might either be infeasible, or it may be suboptimal, and then you need to continue. And one way to do so is the approach that's been implemented in a solver that's called QSOP-X. We term that incremental. So this is not our approach, but when we improved upon this, we call this incremental precision boosting. And that simply means if you realize that the basis is not feasible or not optimal, then the floating point precision that is used to perform the floating point simplex is simply increased from 64-bit to 128, and even further, as long as or until the floating point simplex in higher precision reaches basis information that can be verified to be an exact solution. And one disadvantage of this is that, well, as soon as you boost the precision, of course, also your floating point simplex becomes much slower than the double precision version. And so one improvement upon that we have developed is called LP iterative refinement. And that has a very similar goal, basically to reach a basis that is optimal, but it doesn't do so by boosting the precision, but it uses some supplementary problems that you can solve on double precision level in order to continue pivoting in a more efficient way. And so these, what I've described here already is basically algorithms that use different levels of precision in order to compute exact results. And this kind of theme of using different levels of precision in order to create an efficient algorithm or a fast algorithm is also used in the mixed integer setting. So the fastest method here go along these lines. It's a bit different. So the goal in mixed integer programming is a bit different. We don't always need exact linear programming solutions. Actually, all we need is exact dual bounds. We need the safe underestimations of our optimal objective value. And so we do not necessarily need to solve the LP relaxation to optimality, but we just need to get such a safe dual bound. And so there are several ways on how here you also gain, you compute an approximate solution by a floating point LP solver, and then you somehow try to correct the dual bound in order to be a valid underestimation. And there are two things, two methods that I want to mention here, beyond which are methods that can be used beyond this simple way of using an exact LP solver. And the first is primal bound shift. One way, one name for it, which is essentially that you use directed rounding, sometimes also called interval arithmetic, in order to compute a safe bound. So in order to know what exactly goes on, you have to look at this dual linear program, which I've written here, which is a bit of a handful technically here. But basically what you have written here is that you try to compute the maximum, like the tightest underestimation of the objective function that you can obtain by aggregating the constraints with some dual multipliers. And so basically your floating point solver gives you a candidate Y of dual multipliers for each constraint. But when you aggregate these constraints with these approximate dual multipliers, then you will not be dual feasible. The dual feasible constraints are exactly these equality constraints that are written here in this formulation. And so you need to perform some correction, and the correction that bound shift performs is on these lambda and mu values, which can very easily be shifted when you have variables which are bounded. And so, yeah, if we have, for instance, in the case of an binary program with only binary variables, the bounds are 0, 1, this all works very nicely. In the very general case, however, this may fail. So general MIPS just may have unbounded variables, and then you cannot just do such a simple post-processing. And one more expensive method that was developed in order to deal with this general setting is called project and shift. It also performs such a correction, but it needs a bit more input. So it requires that at the root node, you pre-compute a dual array, so a vector y, lambda, and mu that satisfies these dual feasibility constraints with right-hand side 0. And then you can use later at the nodes of the subtree, you can use this dual array in order to manipulate your floating point dual solution to satisfy the inequality constraints on the dual multipliers, because all these dual multipliers need to be non-negative. And so such a dual array allows you to preserve the feasibility of the dual constraint and manipulate and basically make all the y's, lambdas, and mu's non-negative. Of course, there's also the question, how do I achieve feasibility of this equal z constraint? And also for that, I need to pre-compute somehow matrix inverse to be able to perform a projection. That's why it's called project and shift. So it has this two phases. And so Of course, there are many details, but yeah, what you should take from this is there is a very simple method that may fail for some problems, or may fail also for some, I mean, it may fail at some subnodes of a branch and boundary. And there is a more expensive method, which works more generally. And what is not on this slide, there's a third method, just a total fallback of using an exact LP solver to compute dual bound. This all was combined in 2013, or in the years leading up to 2013, to I guess what was considered the state of the art for exact rational mixed integer programming. This was a version or an extension of the skip solver by Bill Cook, Thorsten Pochte, and Steffi and Kati Wolter. And it is such a hybrid precision LP-based branch and bound, where different of such safe dual bounding techniques are implemented, and they're used in a hierarchy. Of course, you first try to use the cheap ones and then the more expensive ones. They have implemented state-of-the-art branching heuristics and measured that the result is about a factor of 2 to 4 times slower on average than the floating point version. So this seems to be actually quite a very good result, right? Only a factor of 2 slower, although you have this additional effort of creating safe dual bounds. But one thing that you need to know about this is that this is, of course, a comparison to a plain branch and bound. So this research was performed on a version of the solver which did not include a lot of the sophisticated techniques that actually make MIP solvers fast today, that make floating point MIP solvers fast today. And so while they had the state of the art in making the right branching decisions, it did not include cutting planes, conflict analysis, pre-solving or primal heuristics. And it did also not include the this LP iterative refinement scheme for solving exact LP relaxations exactly that I've mentioned. And so 3 things are now what we have worked on in the last 2 years to bring this up to date. So we don't have exact cutting planes yet or exact conflict analysis yet, but we have included this iterative refinement LP solvers. We have included rational exact MIP pre-solving, and we have included primal heuristics. And this is what I would like to talk about now in the next section on what the impact of these techniques on an exact MIP solver are. Are there any questions at this point?
I don't see any questions in the chat. What I am thinking about is at this point in time, we would normally take a short break.
It's already 6:45. Yes, yes.
Yeah,
okay.
So I'm thinking like maybe should we do?
I mean,
5
this is
to
a good
10
point
minutes?
to take a break.
Yeah. So what does the speaker suggest? Do we do 5 minutes, 10 minutes?
That's not up to me. That I think depends on the audience.
Let's go for 8 minutes. So we'll reconvene 18:55 European time.
Okay, thank you very much.
5 minutes to the hour. Okay, thank you, everybody. So let's see, any questions that have accumulated meanwhile during the break? Anyone has anything that they want to say in the chat or unmute and speak? Okay, I guess there's a question from the YouTube chat. Would it be possible to pre-calculate the worst case denominator ahead of time and then convert
Yes.
the bounded fractional LP into a pure ILP?
Oh, can you repeat the second part of the question?
Yeah, I'm trying to read here. Calculate the worst case denominator ahead of time and then convert a bounded fractional LP into a pure ILP and solve that using infinite sufficient precision integers only. But you wouldn't, then you're turning
yes,
an
first of all,
LP into an ILP, right? But yes,
it is possible to compute the worst denominator ahead of time. That's given by Hadamard's inequality. So you basically have to look at, I mean, Kramer's rule gives you that the denominators are determinants of square submatrices of the constraint matrix. And these are bounded by the product of the norms of the column vectors. These is a really bad bound. So it's going to be huge. But you can use that to multiply the constraint matrix, I guess. Yeah, so I think it would be in theory possible. I don't think that would work for any but small problems.
Okay, fair enough. So I guess it's time to get started again.
Okay, thank you. So here's just a slide on what I've just said. Like, these are the updates that we have made to the last version from 2013. And now begins a tricky part of the talk because it's a part with many computation results in tables and it's easy to get lost. I will try to point out what are the important numbers. And my focus here is not to show, oh my God, we've got so much faster, but really like, what have we done in order to get faster and to analyze these results? So this is not the motivation here is not benchmarking, but getting insight in what costs time and what not. So the first step that we've done when we took on the kind of old proof of concept code was a revision of the basic branch and bound framework, which also includes the use of a new exact LP solver based on this LP iterative refinement, that is, we use Simplex instead of QSOP-X. We can now use the project and shift method more aggressively because we have a better LP solver, I would say. And some smaller technical things like enabling the objective limit in the floating point LP solver and faster feasibility checks. These are details. But so what are the results? You see here a comparison between the original framework and the new framework. And you see two lines which correspond to two different subsets. These are from the original paper, 2013. So there's one set which is easy for the floating point solver, 55 instances, called FP easy. And there's one set which was identified to be to have really numerically difficult instances, so where floating point solver really runs into trouble. And we will now continue analyzing the results on these two different subsets. You see that we, like in the first columns, solved that we solve more of these instances now, really to prove an optimality. And mostly you see that the time has reduced drastically. So from 128 seconds to 38 on FP easy and 237 to 46 seconds. So that's a massive speed up. it only comes partially from smaller trees. So you see the number of nodes have not been reduced so significantly. So really a lot of the simply node processing time has been reduced. And this is also what you see in the last column, the column dB time, which is the time that is spent for these safe dual bounding methods. So for the algorithms that convert an approximate floating point dual bound to an exact safe dual bound. And so this is really where the speed up comes from here, because this has gone down from almost 100 to around 10 seconds in the new framework.
So this is times are an aggregate for all instances, or like
Yes,
median
so
time, or?
no, what we use that's pretty standard in MIP solving are shifted geometric means. So in order to account for the fact that, of course, for different instances, the magnitude of solving times vary. So the geometric mean can handle that. But then sometimes there's a problem because you overweight the importance of instances with very small running times, and these are actually not the most important ones. So we use a shifted geometric mean, so a geometric mean on times where we add like 1 or 2 seconds as an offset. Yes.
Okay, thanks.
So because the speed up has so much come from the improvements in these dual bounding methods, here is a more detailed table which shows you how much time was spent for the 3 different most important methods. And this is this bound shift, which is the super fast one that may fail, the projection shift, which is more expensive, and the most expensive method, exact LP. And what you see is that so there are many things to see, and I don't want to go into all the details here, but let's focus on the first line, which is the average calls per node. So how often was one method used? And so here you see that bound shift has been used much less, and that is an engineering artifact because we now deactivate bound shift when it fails very regularly. But we also see that primal shift is called less, and the reason is because bound shift is actually, when it's applied, it's more often successful because we are a bit more clever about aborting with respect to unbounded variables. So there are cases when bound shift can be used also when unbounded variables are present, and we exploit this now. And then most importantly, exact LP solving is called much less often, and that's one of the most expensive techniques. And so that also really reduces the overall running time. Maybe one strange thing is the second line. This tells you how much time is spent per call for these bounding methods. And there you see in the original framework, project and shift was, I mean, these are small, very small numbers, 0.002 seconds per call, while this is tripled in the new framework. So why would that be the case? That's reason is because project and shift is now, so in the old framework, there was a working limit for using project and shift because it simply could not be applied to large scale LPs due to the limited performance of the exact LP solver. And now with Simplex, we can actually use it for much larger problems, but that also means that the average times go up, but that's actually a good thing. So yes, so overall, we notice we need to use the exact LP solver much less, and project and shift is much more successful. But yeah, let's step to the next part. That is algorithmically maybe a bit more interesting, and that is the addition of rational pre-solving. So let's look at the results first. So the new framework without pre-solving, and then when we enable rational pre-solving, we see increase in the number of instances that are solved on both test sets. Not huge, but noticeable. But most of all, we see a reduction in the running time and a reduction in the number of nodes. So here it's much more the case that actually the reduction in the running time also comes from a reduction in the number of nodes. And that shows you that pre-solving does not only reduce the size of the problem, but it really strengthens the formulation. It makes the dual bounds much tighter, and then as a result leads to much smaller enumeration trees. And you see that in the on the right side in these parentheses pre-solving, that the time needed is really small compared to the running time. So it's a cheap step to make a big improvement. How was this achieved? So we've done this externally by creating a new software library for pre-solving independent of skip. And one thing that we did from the beginning is that we simply templatized the arithmetic type that is used. So we can simply plug in GMP for all of the operations, and then automatically we obtain a rational pre-solver. One other nice feature about this library is that it allows to parallelize the techniques that are run. It cannot parallelize the arithmetic operations themselves. So you should also not expect that this linearly scales or something or anything, but it can kind of buffer some of the computational overhead that you get when you use rational instead of floating point arithmetic. And this is what you see here a bit in this detailed table. So there we have for each test set one line for one thread and 20 threads. And what you see in the right side exact pre-solving time column is that the times are reduced slightly. So from 0.25 to 0.14 on average, which is not at all a great parallel result for using 20 threads instead of one. But it's still something nice to have. And there are individual instances where the kind of the worst case running time is reduced significantly. One thing that is that you can see in this table here is basically how does the exact pre-solving compare to floating point pre-solving, and not only in time, but also in the amount of reductions that it obtains, because a priori it's not at all clear whether an exact pre-solver would have result in more or in less or in the same amount of reductions, because some reductions can be applied more aggressively when you do not need to worry about tolerances. Some will be applied more conservatively because you cannot decide whether something is exactly, like whether two columns are exactly linearly dependent. They're just not. And so one surprising result here is that actually it's very, very similar. So the number of rounds, the number of fixings, the number of aggregations, which you see in these three columns in the middle, and the number of bound changes for the easy instances are identical. This is not an error in the table. And what you see when you look at the numerically difficult instances, that there are, of course, differences. And you see on the numerically difficult instances, actually, you find a bit less fixings, a bit less aggregations, and a bit more bound changes. And that simply means that the exact pre-solver is truly a bit more conservative and more correct, because floating point pre-solving probably just did incorrect reductions on the numerically troublesome instances. Okay, so this is a nice and apparently very, very helpful and important technique to also have in exact solving, especially for these difficult instances. Then let's come to the third algorithmic part, and that is the addition of primary heuristics. And again, let's first look at the results, and then let's look at how we actually obtain these results. So we compare here again disabled and enabled heuristics for these two test sets. And the first disappointing thing that you see is that the solving time is barely affected. on numerically difficult, it actually slightly increases. I mean, barely noticeable. So why? Well, actually, this is an effect that is not so surprising. It's something that also in floating point MIP solvers can be observed, that actually primary heuristics, when you only look at the time needed to solve to optimality, are not very important. So in floating point heuristics, floating point solvers, I think you see that I think one measurement was like 14%, that you can speed up solvers by about 14%, which is also not a huge number. So here we basically have no speed up, but what we see is that the time to obtain the first feasible solution is significantly reduced. And that's quite interesting, because that makes these solvers also more useful in practice. And so now, how did we actually implement these rational heuristics? Well, we did not implement rational heuristics. We took a meta approach by doing the following. We execute floating point heuristics like they would be executed in a floating point solver. So they run on the floating point representation of the problem. And then if they are lucky, they return a feasible solution, approximate solution. We can first of all check whether we are lucky and they are actually feasible. Often this will not be the case. It does happen sometimes, but often not. And then we can try to repair these approximate solutions simply by fixing the integer assignment after rounding the values, and then calling the exact LP solver on the remaining linear program. And this is potentially, of course, expensive. So what we do is that we buffer. We try to buffer incoming solution candidates until we reach 10 solutions, or until like the potential improvement is huge. So that we do not actually call the exact LP solver too often. So there is a bit of sophistication in it. One motivation for not re-implementing all the heuristics in arithmetic is not only because we were lazy to do so, but because the rationale between heuristics here is, of course, as I've mentioned it, is very similar to the floating point setting. Heuristics here should not be as aggressive as possible, but they should somehow have a limited effort and try to be successful when they can for within a small computational budget. And that simply means that, for instance, running a sub-MIP heuristic in rational arithmetic would just is not called for. And so this approach of just running heuristics in floating point and then trying to convert a solution seemed much more reasonable to us. We of course see that this has limitations, especially when we look at the second line here for the numerically difficult instances. So because well, this is actually the next table, yes. So where we in this table you see a bit more how these heuristics or how this approach performs, and there you see in the second table that the success rate is that the success rate is much lower here in the very last column than for the instances which are easy for the floating point solver as well. And that of course indicates that running floating point heuristics on numeric difficult instances just well, the instance is just is not as representative of the exact problem as in the other test set. And so for these numerically difficult instances, it might be reasonable to think about designing some more dedicated rational heuristics in the future. Okay, so this was the third part on primary heuristics. We see that doesn't really help to solve to global optimality, but is very nice in terms of getting primary solutions very fast in the beginning. And now at the end, I would like to show you some numbers on more recent test sets. So this was the test sets that were rather small, as you could see. And so we've also compared now the full-blown new version with the original framework on the MIPLIB 2017 benchmark set, which is the current standard for comparing floating point solvers. There you see, well, you see similar results than what we've seen, what could be expected from the previous tables here. So the original framework, in the first line, you see like statistics over all instances that instead of 17, we can solve 47 now to proven optimality. And for many more instances, we find actually feasible solutions. That's due to the primary heuristics, really. And the running time is also significantly reduced. Not only the running time, but also the gap at termination. In order to evaluate this, we need to restrict ourselves to the instances where we actually have a finite gap for both codes, for both frameworks. This is in the second line there. You see also the gap on average here is reduced by a factor of 2. And now, what does the last line mean? So the initial line averages over all instances. That means also over all instances where both solvers time out. And of course, in this benchmark set designed for floating point solvers, there are a huge number of instances which are, I mean, they are even hopeless for floating point solvers, so they are more than hopeless for exact solvers. And so in the last one, we excluded all the time or the double timeouts. And there you see that the speed up is much larger. It's not only a factor of 2 like in the first line, but it's a factor of over 6. Yes, so this kind of gives you a snapshot of the performance impact of these techniques in the exact setting. And then I have a last table for you that may also lead to some further discussion, as Jakob has already requested. And that is in this new version, we've also included now the printing of certificates, so what I think is called proof logging in the SAT community. I can tell you more later about how these certificates actually look like. They basically encode the branch and cut tree, also in a bit of a special form. Here, they do this in a very straightforward way. There is not terribly much sophistication in it, but here we simply measured like how much overhead does this produce. And so overhead comes in 2 ways, of course. First of all, overhead in solving time while you're printing the certificate, and then overhead to check the certificate at the end. And you see that this checking time is completely negligible. The reason is because the certificate encodes all the information that you need to do so. You only need to recompute it essentially. As on the downside, you see that the solving time increases by a factor of 2 almost, because a lot of dual multipliers essentially need to be printed. And not only because of that, but also because some of this information that needs to be printed is not available for like the fastest dual bounding method, this bound shift method. So this is also why the certificate printing currently requires to do more arithmetic work during the solving, and that's why the time for the dual bounding, so this dB time, increases, as you can see in the dB time columns. We have
Can you say anything about the proof size, like the size of this certificate?
No, I cannot. So I don't have any statistics on that. I don't think we had. Well, we impose memory limits, but no, actually, so since we print everything to file, there's also not really a limitation on like we can now not solve one instance. But certainly they are potentially large for some.
But yeah. I mean, it's an interesting trade-off. I think that also for CDCL SAT solvers, where like some early formats were writing down pretty much all of the information needed, and that makes for fairly big proofs that are expensive to produce. And now I think the tendency has been to shift much more work to the proof checker, so the SAT solver sort of provides the bare minimum and then dumps a lot of work on the proof checker to reconstruct things that the proof checker should be able to figure out.
Yeah. Yes, I mean, as you see, this table says we need to go exactly in that same direction. I mean, this is the first certificate system that has been proposed for MIP. And we do have some ideas on how to go in that direction that you mentioned. But yeah, this is definitely a lot to do there. Yeah, so these are just some statistics for the certificate printing, and then maybe to wrap up now. So what I think has become clear is that the round-off error-free solution of MIPS is still far from competitive with state-of-the-art floating point solvers in MIP. But I hope I convince you that this is quite an interesting area of research to invest time in, and also that what you've seen is that there are no fundamental roadblocks to doing so. So I mean, you've seen the use now of heuristics and presolving and things. It's not theoretically difficult. It needs to be done, and it can be done, of course, in more and less sophisticated ways. But there's no reason why there should not be a exact MIP solver that is within constant factor of slowdown compared to a state-of-the-art MIP solver. So for this old solver, they measured a factor of 2 to 4 respect to the plain branch and bound version. And I think that this slowdown of 2 to 4, that can definitely also be kept for when you include all these state-of-the-art techniques, because most of them are heuristic in nature. So actually you can perform a lot of these things not in rational arithmetic. So the speed up that you gain should be the same or even more than in the floating point setting. And yes, so with this revision that we've done now, this exact extension of skip will also be much more easily available and usable. So if you have any interest, check it out. Thank you very much for your attention. Yeah, so the time was just flying. So I don't know how much time we have now to go into any further details. But I wanted also to thank you for the questions. They were all interesting questions.
I guess, yeah, we did our best to slow you down. But let's see. I think the first question is maybe if there. I see I missed a question from Mate Sauce in the chat, unfortunately, and I don't longer know exactly what it refers to. Is it fair to consider this technique as a form of what we call pre-in processing in SAT solving? There's no timestamp on this. I just missed it.
Yeah, that must be related to the pre-solving, right? And I think the answer is yes.
I guess that, I mean, yeah, so like, yeah, MIP solvers do pre-in processing, but they call it pre-solving. Any other questions, comments? I mean, it is getting there. I'm personally curious about this proof format and what like the proofs look like, but I don't know if it's realistic to say anything about it.
I mean, we do have 5 minutes, right? I mean, there's definitely I can give you a peek.
So I think that unless, yeah, I mean, it's people just log out and leave when they no longer can follow. So in that sense, I guess it's like easier to discreetly slip out of the door than during the regular seminar. So I don't think we need to feel bad going.
I will not be insulted.
So then I don't see any questions. I see a supporting vote for the proof format. and a commitment to listen for 10 minutes before slipping out of the door. Why don't we just go for the proof format?
Yes, that's encouraging. So I think I have to go. Yeah, I had two things prepared, so I just need to fast forward now to the proof section.
I'm sorry to miss this other
yeah,
part.
so that is perfectly fine. So yeah, what's the status quo? Basically, most MIP solvers do not output any optimality certificates, and the reason is not just laziness. It is, of course, there are some difficulties with it, and they go beyond. I mean, the theoretical difficulty that you also have in SAT is that there are no small certificates in general, right? Unless there's a super huge amount of checking them. But practical also in MIP solvers, one problem is that the techniques that are applied are very complex and diverse. And so encoding them in proof can be quite a lot of implementation overhead. And where the certificate form is not like uniquely defined, there are several ones. I mean, the most natural one is certainly the tree certificate. And this is also what we went for in this straightforward suggestion. So goals would be, of course, that a format should be expressive. It should be able to encode all or at least most of the important algorithmic techniques. It should be simple, so checking should not require a sophisticated code that could contain bugs itself. And it has to be somehow general in the sense that it applies to all MIPS and not only to a special subclass, which, I mean, there have been works for the traveling salesman problem, for instance, in the optimization community. And so, yeah, as I said, our suggestion was quite straightforward. So LP bounds can be simply certified by a dual solution. That's quite simple theoretically. So here you have this small example of an objective function and two constraints on two variables. What we derive as an optimal solution can be certified by creating using the right dual multipliers to add up these constraints to obtain the objective function. So here, for instance, if you take 1 times the first constraint and -1 times the second constraint, then you obtain 5 minus 3 is 2x, and -y plus 2y gives +y, and greater than or equal to 2. And here you have less than or equal to 1, so that of course turns around. So greater than or equal to -1, if you add that up, 2 minus 1 gives 1. So you obtain these constraints, which must certainly be satisfied by all feasible solutions. And so they must all be greater than or equal to 1. So that's just plain LP duality. And so now if you provide also a primal solution, then you have basically a certificate of optimality. And in plain text syntax, this Viper format would look the following. You first of all specify your problem by stating the variables. You specify the objective function. We do this in a very non-human readable way by just indices and coefficients. So variable 0 has coefficient 2, variable 1 has coefficient 1. And we do this sparsely, so because later for the constraints we will definitely need a sparse representation. So we say here already the objective function now has 2 non-zeros. We do the same for the constraints. There we have to also encode the right side, so greater or less than or equal to the right-hand side of 2. And I think here's an error that should be a 1 here. And then we somehow should tell you what we want to prove. So here we want to prove that the range of the objective function is from 1 to infinity. So we now derive one constraint, which is the objective function constraint, 2x plus y greater than or equal to 1, which is encoded here like in G1 for the right-hand side. Then two non-zeros. The zeros variable has 2, and the first variable has coefficient 1. And we also have an abbreviation for not always writing this same pattern, which corresponds to the objective function. And then what you need to tell the checker is how did you obtain this, kind of the certificate for this LP duality. And there we say, we have a keyword saying lin, which is a linear aggregation of constraints. Here it says that we aggregate two constraints, namely the 0th constraint with a multiplier of 1 and the first one with a multiplier of -1. And then we simply, if you want to also have a primal solution in there, then we just need to add some section for how the primal solution looks like. That's of course simple. And then we can not only give this range 1 to infinity, but yeah, that the objective function value is actually equal to 1. So I guess that is very clear. So very, very straightforward. So now we've not talked much about cutting planes, but of course cutting planes should be somehow possible to encode in such a certificate. And for that we need some sort of rounding operation. So here's again a different problem, and the class, so many cuts. So for instance, Schwatter-Montgomery cuts can simply be derived by forming again an aggregation such that all integer variables have integer coefficients and continuous variables don't appear, and then round up the right-hand side. And we do this here in 2 steps. First of all, we create the aggregation. Here, y greater than or equal to -1/2 when you use 1/2 and -1/2 for the constraints. And then we explicitly have a rounding step of saying round up the right-hand side. This is a separate constraint. And this you can then continue, of course, also, and you can use the previously generated cuts. And so in plain text syntax, that would look like this. We have then a keyword R&D, which corresponds to rounding the right-hand side. And then, yeah, not only cutting, but branching is important. So how do we encode disjunctions? So we did not want to explicitly encode a tree structure. So really to have a relationship of parents and children and whatnot, because that is just a pain to keep track of for a checker. And also there are cuts that might actually use disjunctions that are not in the tree. And so we simply have lines that encode the disjunctions that we have. These are not certified. These are just a list of disjunctions that we may use later on. These are just general linear inequalities. And then you can derive something based on these assumed distinctions, on these assumptions. Then, of course, you may end up with derived constraints, which are valid only with respect to some of these assumptions. And so what you need is somehow a reverse operation, which tells you, I have now proven something for 2 disjunctions, or for disjunctions, like for 2 assumptions, which as a union form like the whole solution space. You have 2 identical derivation constraints, C3 and C4, and that both are valid without the opposing assumptions. And so we have kind of an operation which we called unsplit. So we had 2 parts from a disjunction and derived certificates, derived constraints for each of them, which are the same, and then we unsplit them and say they are valid now for without these assumptions. And so this would look like, I don't have the plain syntax here, but I think you get the idea. So we only have basically 4 reasoning types. I mean, one is not even a reasoning type, it's just an assumption. We have no explicit tree structure, but as a result, we can check each line sequentially depending on the previous lines. Theoretically, the question is now, can we express sort of all the reasoning that MIP solvers do? And on the cutting plane side, what the right picture here should tell you is stolen from a paper that proves that basically most interesting cuts can be expressed as so-called split cuts. And split cuts are simply cuts where you use the disjunction and then prove the validity of an inequality for both sides, and then you have proven the validity for without the disjunction. And so, for instance, Gomery cuts can also be proven like this. And so in some sense, for cutting planes, this certificate would be quite expressive. And I think also for things like presolving and propagation techniques, not counting symmetry, it would work, or for other techniques. Yes, I think that was now everything that I had prepared anyway for this. And if there are
so
questions.
question about certifying different types of cut rules. So if you want to do mixed integer rounding cuts, then is it right that you would somehow do like do a disjunction or like branch on some variables and then certify, and then what was it called, like unsplit, or how do you how do you do in general like a mixed integer rounding cut, and how efficient would the certification step for that be?
Mm-hmm. Yeah, so we've not implemented anything on cutting planes. So the reason is because the current version of the exact skip simply does not have exact cutting planes yet. And so we have no comparison on like now what would be the most efficient way to do so. But yes, for mixed integer rounding, you would definitely have to create the disjunction. And so there is certainly an overhead. So you should not expect that you can now use 1 or 2 lines for expressing the validity or for certifying a mixed integer rounding cut. Yeah.
Because there's like one you can, there's a trade-off also what you accept as your primitives. Like if you expect to use mixed integer rounding cuts often, then should you like put them in your base language and just say that we accept them to be true, or do you prefer? I mean, the rounding rule you had is like extremely clean and simple, right? It's clear that it's valid. Whereas for me, mixed integer rounding cuts are still very mysterious.
Yes. No, so I think what we need in the end is sort of a hierarchy of certificate formats. We need one that is that can contain a lot of special reasoning types, just in order to allow the solver to print them very quickly without having to recompute anything. But then I would say checking these safely without bugs is probably a bit tricky. And so we would need probably some tools to convert this into a more plain format like the one that I've presented now, such that we can get a certificate that is, of course, potentially larger, but can be checked with much more certainty. So I think this is how we would go about it.
There's a question in the chat, but I see Kieran, we see your video. Is that because you want to ask?
Yes, one more before I have to run off and eat dinner. Does pre-processing for MIP ever introduce or remove variables, for example?
It does certainly remove variables. It does also aggregate variables in the sense that you say X can be expressed as a linear combination of other variables, and then X is removed and replaced by this. Yes.
Have you thought about how you could presolve that?
It does not very much introduce additional variables.
But extended formulations, wouldn't that like introduce variables or no?
Yes, but that's not the kind of standard repertoire of what's used in MIP solvers.
Oh, they're not that common?
no, I mean, they are a big area of research in MIP, but they are not automatically created. I think maybe the thing that would maybe come closest to is what we already discussed, is binarization of integer variables. Of course, if you perform that, that would create new variables, yes. And the certificate format is not laid out for this.
Okay, thanks.
Any other question on proof logging? I mean, we do have a question that I certainly won't drop regarding the how MIP solvers stack up against SAT and pseudo Boolean solvers. But before we move there, anything else on the proof logging? If people are interested, I'm trying to monitor. All these
what I would really say is that in the MIP community here, we are very much in the beginning, and certainly the success, or I mean, just the methodology that is available in SAT and in pseudo Boolean solving is an inspiration for me to improve the situation here.
Okay, so Pratik Chakraborty had a question more about solving, and there was some discussion going on in the chat as you were giving your talks. I'll just read it quickly and then I'll let you comment on it. So Pratik started by asking, this is perhaps a naive question. If I'm trying to solve a largish set of pseudo Boolean constraints, so 0, 1 integer linear constraints, when, if at all, would it potentially be beneficial to try out a MIP solver, say skip or Gurobi, instead of a PB solver like rounding SAT or SAT4j? To which I answered, the answer is very painful most of the times as things are looking now. Not always for sure, but commercial MIP solvers are very, very good. And even skip beats rounding SAT and SAT4j on the pseudo Boolean competition benchmarks from 2016. There are problem domains where PB solvers are better though, and for CNF problems, so problems in conjunctive normal form, MIP solvers tend to be pretty bad, I think. And then Supratik wrote back, I see. Are there some rules of thumb to help choose? Is it mostly the enormous amount of engineering that has gone into skip Gurobi that explains this? This is, of course, not to discount the tremendous effort that has gone into rounding SAT/SAT4j as well. So that's the discussion we had, and now I guess it's your turn to comment on this.
Yeah, so I would subscribe to what you said. I think one rule of thumb is if it's an optimization problem, go for a MIP solver. I think they're just more geared towards optimization problems. If it's a plain feasibility problem, I mean, pseudo Boolean solvers might have a shot at being the fastest. One bottleneck for MIP can be if the problem are really huge and dense, for instance. I don't know if that happens in pseudo Boolean or if you only consider sparsity, but if they are really dense, then the linear programming simply may become a huge bottleneck, and so MIP solvers may not be very good, simply because, yeah, they don't even get started. And maybe just one more thing that doesn't answer the rule of thumb question, but I think we of course need to acknowledge that the comparison between pseudo Boolean solvers and MIP solvers is not fully fair, in the sense that MIP solvers are not exact solvers, right? Pseudo Boolean solvers are numerically exact, while MIP solvers are not. They may also return a solution that's, yeah, I don't know, slightly infeasible or that's suboptimal if you have numerically troublesome problem formulations. And so probably the more fair comparison would be to compare it to this exact version of skip that I've presented to you, and then also things might look a bit brighter for pseudo Boolean. I don't know. Depends on how important exactness is, of course, for your problem, for your pseudo Boolean problem.
I think it's definitely the case that the current state of the art, as you said, Ambros, that for decision problems like rounding SAT and SAT4j would have a shot. For optimization, you know, we really struggle. There is, I think this is an interesting, you know, if we would all have met at the Simons, then one thing I think we would have been talking about is I think there are a lot of interesting ideas on the MIP side and some other quite interesting idea on the SAT/pseudoboolean side, and you can think about whether it would be beneficial to combine the two. For instance, the conflict analysis on the pseudoboolean side is potentially quite interesting. But this idea of solving LP relaxations and adding cutting planes on the MIP side certainly seems to be very, very powerful. And I think it's probably, I mean, MIP solvers are used a lot in industry to, I think every self-respecting airline is like, I guess, running MIP solvers every day.
Yes.
Well, not now because they're not flying now, but, you know, pre-pandemic, they would schedule their flights and their stuff and everything. And so I think probably like the man years that have gone into MIP coding is, you know, orders of magnitude, I think, more. Whereas, so, but I think there's room for doing work at the intersection of SAT and MIP, and that's sort of where pseudoboolean solvers would sit. And then you should also not forget about MaxSat solvers that are really, really good, but they're essentially, I mean, MaxSat solvers are essentially pseudoboolean solvers, but where you insist on that you only want to deal with CNF, conjunctive normal form. So that's a third paradigm to check out. And we do have, I mean, this is shameless self-plugs, but there are some recent papers involving my research group, among others, that where we can see that if you take ideas from MaxSat, from pseudoboolean, from MIP, and you mix and match, then interesting things happen. Other questions, comments? I mean, this was an amazing talk. This was super useful and interesting, and especially
thank you also really for your patience. And for the attention.
I can say so. I don't know if there would be a analog on the MIP side. One thing that has been very important for certifying solvers for like graph solvers, which Kieran McCreesh has been working on, but he ran away. So one thing that was really crucial there was that sometimes the solver, it sort of, you mentioned something analogous, that sometimes the solver knows things, but maybe it doesn't know how to express them in the proof logging formalism. Like, you know a fact, but if you have to write down a derivation, then maybe you don't have that information handy and you need to do more calculations.
Definitely happens.
And this was a big pain for graph solvers because they do bit parallel operations. And at some point they just realized that, okay, the domain of this variable is empty. I have to backtrack. But you don't know why that happened because you did a lot of bitwise ands and ors, and suddenly something happened. And then like a key feature of SAT proof logging that turned out to be very fruitful to lift to graph solvers was this concept of reverse unit propagation clauses. So basically, this is just a fact. So it's easiest to explain for clauses, but a reverse unit propagation clause is like, given the state of knowledge that we have right now, here's a clause that I claim is true. And the way to verify it is I don't tell you why, but the proof checker can check it by asserting the clause to false. So take the minimal assignment that falsifies the clause, and then it just checks that indeed this propagates the contradiction. And now, since assuming that the clause is false propagates the contradiction, then you know the clause is valid, and you can add it.
Just for clarification, or as a question from my side. So this, of course, requires that you do have somehow a verified SAT solver to run this, right? You must have a SAT solver that you trust.
I must have the algorithm for unit propagation. I mean, unit propagation is a very limited kind of, it's an extremely stupid, it's not a general SAT call.
Yeah, okay, unit propagation, okay. Yeah.
So it's only unit propagation that you only fire when a clause has all literals falsified except one, then you set the next one. And you do this until saturation. And if this leads to contradiction, then you accept the clause. But if it doesn't, then you just say, well, I don't know, then it might still be true, but you're not accepting it. So it's like an extremely limited form. Yes, sorry, Stefan.
As you already said, Ambros, I mean, one could also think of having like multiple layers, and you have like the unit propagation layer higher up, which is more easy for the solver to use. But if you want more trust, then you can like transform the unit propagation into some simpler language that doesn't do any automation, but really writes down explicitly what you need to do to get these steps of reasoning.
So, I mean, one idea that we had, I don't know if that goes beyond. But so to do something analogously, that these dual multipliers for the LP certificates are actually, you do not need to print. If you do it correctly, then you can just use an LP solver to recompute them.
Yeah.
That would be, I think, a similar thing.
So what I've also been thinking about that, but I fear that this would be too expensive somehow, like to run the LP solver for verifying every step somehow. But maybe it also depends on the application. I guess in MIP solving, where the result was obtained from a LP solver in the first place, then maybe it doesn't matter too much. Because like you're again like in the same running time as the solver.
Yes.
But like, but also like, I mean, when like in sometimes we are trying to handcraft kind of linear combinations for writing down proofs, and this is really annoying thing to do.
Yeah, this is also what I would like to, especially for all these different pre-solving techniques where you know that's true, but writing this down as a dual proof is just annoying.
So I think we should probably, start thinking about wrapping this up. There is one more question, I think, in the YouTube chat, which I interpret as follows. I don't know if I'm interpreting correctly, but when you're branching in a MIP solver, so something that people on the theory side have been looking at is branching on generic linear inequalities. Like you take some linear combination, vector A times vector X, and you branch on whether this is larger than B or smaller equal B minus 1. Are these kind of general branching decisions something that MIP solvers would do? Or is it just like more theoreticians thinking about this?
It has been investigated in the literature. Currently, solvers don't do this. There are several reasons why it doesn't seem beneficial. So the first one is simply, it's much harder to figure out a general disjunction. So you just need to spend much more time. Was there a question? Yes. So anyway, the first bottleneck is degree of freedom is huge. So and there are no good ways to actually limit this currently. We need better ideas. And the second, that if you use general disjunctions, then the LP solving gets slower. Because if you do variable branching, you fix variables, so you reduce the size of your LP. When you would do general constraint branching, you add constraints, so you slow down the LP. And that doesn't seem to pay off in practice. Also, of course, the dual bounds could improve. Mm-hmm. But there are several papers which have tried. I also have one.
I see. So on behalf of all the audience, let me just thank you again for a fantastic seminar. This is great. Yeah.
Thank you very much for your patience and attention.
And we should say that we have another MIP talk coming up. I think I'm struggling to think now, but May I don't remember 11th, when.
I believe.
Oh, yeah. Let's see. So yeah, on May 11th we have another MIP talk, and of course before that we have so this I should have said at the outset, but next Tuesday we're talking about answers at programming, which is another paradigm that is sort of goes beyond SAT. And then in 2 weeks from now, something that we briefly touched on today, namely in 2 weeks from now, we're going to talk about maximum satisfiability solving, or MaxSat solving, which is sort of also pseudo-Boolean solving or 0-1 interlinear programming with another name, and focusing on constraints in conductive normal form. But I think this is it for today. Thanks, everybody.
Thank you very much.